Okay, so this is a video of some frequently asked questions in the um, Unit 3 review. All right, so first question, number 4. For the function f of x equals natural log of x over 9x, find the second derivative. Then find f double prime of 0 and f double prime of 5. So first off, let's take the first derivative. And I'm going to use the quotient rule. So the derivative of the top, which is 1 over x, times the bottom, 9x, minus the top, natural log of x, times the derivative of the bottom, which is 9, all over the bottom squared, which is 9 squared x squared. And now what I'm going to do is I am going to get rid of a 9 from each term because there's a 9 in each term. So I'm getting rid of a 9 here, a 9 here, and 9 here. Now, when I have a 1 over x times x, that just gives me a 1. So I get a 1 minus natural log of x over 9x squared. So now let's take the second derivative. So the derivative of the top, well, the derivative of 1 is just 0, and the derivative of negative natural log of x is negative 1 over x, times the bottom, so times 9x squared, minus the top, so 1 minus natural log of x, times the derivative of the bottom, 18x, over the bottom squared. So again, 9 squared, this time x to the 4th. So again, I'm going to get rid of a 9 in each term. So I get rid of a 9 here. When I get rid of a 9 here, I end up with a 2. And here I just end up with a 9. Now, when I reduce the negative x times x squared, this time I'm going to be left with a negative x minus 1 minus natural log of x times 2x over 9x to the 4th. Now notice we have an x in every term. So I'm going to get rid of an x in every term. So this is going to become a 1. That will become a 1. And this will become a cube. So I have a negative 1. Let's go ahead and distribute this 2. So minus 2 plus 2 natural log of x over 9x cubed. And I end up with negative 3 plus 2 natural log of x over 9x cubed. So that's my simplified version of the second derivative. Now, they want us to find f double prime of 0, but that's going to be undefined. I can't plug it into the natural log of x, and I can't plug it into the denominator. So that is undefined. And then the second derivative at 5 is approximately 0.0002. All right, next problem. Find the open intervals where the function f of x equals natural log of x squared plus 49 is concave up and concave down. So we know that we find concavity, the second derivative. So I'm going to take the first derivative, then the second derivative. So remember, taking the derivative of natural logs, you take the derivative of the inside and put it over the inside. So the derivative of the inside is 2x, and the inside is x squared plus 49. Now let's take the second derivative. The derivative of the top is 2 times the bottom, x squared plus 49, minus the top times the derivative of the bottom, which is also 2x, over the bottom squared. All right, and notice the denominator, there's nothing that I can plug in the denominator that'll make it undefined. Let's go ahead and distribute the 2 in the numerator. So I get a 2x squared. What does that give me? A 98 plus 4x squared over x squared plus 49 squared. So I end up, I'm going to set this equal to 0, right? Because I'm going to look for inflection points. It gives me, whoops, this should be negative. Negative 2x squared plus 98 over x squared plus 49 squared. Right, multiply both sides by the common denominator so that I'm just left with 2x squared plus 98. So negative 2x squared plus 98, move the 2x squared on the left side, and I get x squared equals 49, and I get x equals plus or minus 7. I'm going to put these on a number line. If I plug in 0, I can see that I'm going to get something that's positive. Whoa, I don't know what that is. All right, if I plug in 0, I know I'm going to get something positive. So I know it's concave up there. Now, if I plug in something less than -7 or bigger than 7, then this term is going to trump the 98. So I'm going to get something that's negative. So it's going to be concave down here and concave down here. So I know that I have points of inflection here and points of inflection here. So f of -7 is the natural log of -7 squared plus 49, which is the natural log of 98. So I have the point -7 natural log of 98. And f of +7 should give me the exact same thing. Natural log of 7 squared plus 49 is natural log of 98. So I get the point 7 natural log of 98. All right, and we are concave up on the interval -7 to 7, and concave down on the interval -infinity to -7, and from 7 to infinity. All right, next question. So suppose that the graph below is the graph of f prime of x. All right, the derivative of f of x. Find the open intervals where the original function is concave up and concave down. All right, so what I need, so they give me the derivative of f prime, and I know again that concavity, I find concavity at the second derivative. So I'm going to take the second derivative. I get 4/3 x cubed minus 9x squared minus 14x. All right, I'm going to set that equal to 0, and I'm going to factor out an x so that I have a 4/3 x squared minus 9x minus 14. All right, so I know that x equals 0, and then I'm going to use the quadratic formula. All right, so I have negative b plus or minus b squared minus 4ac all over 2a. And I wrote this down earlier. Let's see where I put it. All right, so end up getting 9 plus or minus the square root of 467 over 3 divided by 8/3. And that gives me approximately 8.1 and -1.3. All right, so I'm going to put these on my number line. All right, I have the -1.3, I have the 0, and I have the 8.1. All right, they give us the graph of the derivative. I know where the graph of the derivative is decreasing, it is concave down. Where the graph of the derivative is increasing, it is concave up. So I can see that it's decreasing here and here. I think there's a very small portion where it's increasing like in here. So from negative 1.3 to 0, you can't really see it. But from here to here, and then it's increasing from here on. So from negative 1.3 to 0, it's increasing, so concave up. From 8.1 and on, it's also increasing. And in the other places, it's decreasing. So it's concave down. So we have the points of our inflection points because that's where it's changing concavity. It is concave up between negative 1.3 and 0 and 8.1 and infinity, and then concave down, negative infinity to negative 1.3, and then from 0 to 8.1. All right, and that's it. All right, next question. Find any critical numbers for the function x to the 11th minus x to the 6/5 and use the second derivative test to decide whether the critical numbers lead to relative maxima or relative minimum. If the second derivative gives no information, use the first derivative. Okay, so first thing I need to do is I need to find my critical points. So I'm going to take the first derivative and set it equal to 0. So f prime of x is equal to 11/5 x to the 6/5 minus 6/5 x to the 1/5. I'm going to set this equal to 0, and I'm going to factor out a 1/5 x to the 1/5. So I'm left with 11x minus 6. So that gives me critical numbers x equals 0 and x equals 6/11. All right, now I'm going to take the second derivative. And I'm going to take the second derivative from this line here. So I get 66 over 25 x to the 1/5 minus 6 over 25 x to the negative 4/5. All right, and now I'm going to use the second derivative test, which means I plug in my critical points into my second derivative. Now, I can't plug in 0 to my second derivative because it's undefined. So I will have to use the first derivative test on 0. But if I plug in 6/11 to the second derivative, I get something that is positive, which means it's concave up, which means it must be a relative min. All right, so now let's go back to the first derivative test on 0. I'm going to put 6/11 here just to make sure that we pick a number in the correct interval. If I plug in a negative number, say -1, I'm going to get a negative number here and a negative number here. So that's going to give me something that's positive. If I plug in a positive 1/2, I'm going to get something positive here, but something negative here. All right, so this is a max. So relative min, relative max, relative min. right? We had to use the first derivative test on 0. Next question, graph the function, consider the domain, critical points, symmetry, regions where the function is increasing or decreasing, inflection points, regions where the function is concave up, concave down, intercepts where possible, asymptotes where applicable. All right, so I always like to do this in 3 stages. We start with the function, the first derivative, the second derivative. So let's start with the function. First of all, we can state the domain. There's no natural logs, there's nothing in the denominator, there's nothing under the square root, so the domain is all real numbers. All right, there's no vertical asymptotes. There is a horizontal asymptote. However, we don't have the skills in this class to come up with that horizontal asymptote, so I'm just going to leave that off for now. We can go ahead and find the intercept. F of 0 is equal to 3 times 0 e to the negative 0, which is just 0. So I know I have the intercept 0, 0. Now let's look at the first derivative. So I'm going to have to use the product rule. So the derivative of the first is 3 times the second plus the first times the derivative of the second, negative e to the negative x. I'm going to factor out a 3e to the negative x. I get a 1 minus x. So I have a critical point at x equals 1. I'm going to put that on a number line. If I plug in 0, I get something positive, so increasing. And if I plug in something bigger than 2, I get something negative, decreasing. All right, so I am increasing on the interval from negative infinity to 1 and decreasing on the interval from 1 to infinity, which means I can probably get rid of a couple of these graphs. So it looks like this one and this one. Yeah. All right. Let's go ahead and take the second derivative. I'm going to clean the first derivative up just a little bit. So I had 3e to the negative x minus 3x e to the negative x. So my second derivative is equal to negative 3e to the negative x. Now the derivative of the second term, the derivative of the first, is, whoops. So I'm looking at this version right here. The derivative of the first is negative 3 times the second. Minus the first times the derivative of the second, negative e to the negative x, which gives me negative 6e to the negative x plus 3 x e to the negative x. So I'm going to factor out a 3e to the negative x, and I get a negative 2 plus x. So I have x equals 2. I'm going to put that on a number line. If I choose 0, I'm going to get something negative, so concave down. If I choose 3, I'm going to get something positive, so concave up. All right, so I have an inflection point at 2. And the only one that is concave down before 2 is this one, so this must be our graph. All right. Next question. Sketch the graph of a single function that has all these properties. So f prime of x is greater than 0 on negative infinity to negative 4 and 0 to 3. So this means f of x is increasing on negative infinity to negative 4 and 0 to 3. All right, it tells me f prime of x is less than 0 on negative 4 to 0 and 3 to infinity. So that means it's decreasing on negative 4 to 0 and 3 to infinity. All right, D says f double prime is less than 0 on negative infinity to negative 2 and 1 to infinity. That means it's concave down on those two intervals. All right, so why don't we just take a look at these graphs and see if we can eliminate some of these. Let's see, increasing on negative infinity to negative 4. Negative infinity to negative 4. So that one's gone, that one's gone. Okay. Decreasing on negative 4 to 0. It looks like both of those are just fine. This one says it is concave up on negative 2 to 1, right? Because it says the second derivative is positive. Concave up on negative 2 to 1. It says it's f prime of negative 4 and f prime of 3 equals 0. This means there are critical points at x equals negative 4 and x equals 3. And it looks like there are critical points at both of those. And then it says that f double prime of x equals 0 at negative 2, 3 and 1, 4. So negative 2, 3 and 1, 4. So that tells me that these are inflection points. All right, so let's look for negative 2, 3. Negative 2, let's see, 2, 4, 6, 8, 10, 12. So 2, 4. So that would mean that inflection point was right there. That doesn't really look like there's an inflection point there. That looks closer. And then the other one is 1, 4. So 1, 4. And then 1, 4. All right, so we're going to go with D. Okay, next question. Find the absolute extrema if they exist, as well as all values of x where they occur for the function. All right, so remember that if we are on an interval, the absolute extrema either happens at the critical points or at the end points. So what I'm going to do is I'm going to find the critical points, and then I'm going to evaluate the endpoints and the critical points. The biggest one is going to be my absolute max. The smallest one is going to be my absolute min. So let's take the first derivative so that we can find our critical point. So the derivative, I'm going to use the quotient rule. The derivative at the top is 6 times the bottom, x squared plus 3 minus the top 6x times the derivative of the bottom, 2x over x squared plus 3 squared. Are you okay? All right, there's nowhere where this is undefined, so there's not a critical point there where it's undefined. So I'm going to distribute and set this equal to 0. I have a 6x squared plus 18 minus 18x over x squared plus 3. Whoops, 18x squared. So I have a negative 6x squared plus 18 over x squared plus 3. We set this equal to 0, multiply both sides by x squared plus 3, and I'm left with negative 6x squared plus 18. Let's bring the 6x squared on one side, and I get x squared equals 3. So x equals plus or minus root 3. But we're on the interval -3 to 0. So the only one that we care about is negative root 3. All right, so now we need to evaluate each of these. So f of -3, f of negative root 3, and f of 0. So I think I already computed these. All right, so f of -3 gave me -1.5. F of negative root 3 gave me -1.7, and f of 0 gave me 0. So this is going to be my absolute min, and 0 is going to be my absolute max. All right. Next question. A fence must be built to enclose a rectangular area of 20,000 square feet. Fencing material costs $3 per foot for the two sides facing north and south, and $6 per foot for the other two sides. Find the cost of the least expensive fence. All right, so here's my fence, and let's just say that that is due north. So let's call this side X and this side Y. I know that the area, which is X times Y, equals 20,000. All right, this is my constraint function, or my constraint equation. And what I'm trying to do is I'm trying to minimize the cost. I know that the cost is going to be, hey, Fluffers, can you stop? Thank you. The cost is going to be $6 times side X, and there's two sides X. So 2X times 6 plus 3 times the two sides of Y. And that is my cost, and that's what I want to minimize. Now, this gives me an equation with two unknowns. So what I want to do is I want to solve for Y in this equation and plug it into my cost function. So I get 20,000 over X. So cost is equal to 12X plus 6 times Y, and Y is 20,000 over X. All right, so this is what we want to minimize. So I'm going to take the derivative. I get a 12 plus minus 120,000 divided by X squared. Let me make sure my numbers are right. Mm-hmm. 6X plus 12X two sides facing north, and 6 for the other two sides. Oh, I mixed these up. Okay. So let me apologize. This should be 3, and this should be 6. All right, so this should be 6, and this should be 12. So 6 and 240. There we go. I misread. Okay. So we're going to set this equal to 0. And I get 240,000 over x squared equals 6, or 6x squared equals 240,000, or x squared equals 40,000, I believe, yeah, 40,000, and x equals 200. All right, well, if x equals 200, then y equals 20,000 over 200, which equals 100. So we want to know the cost of the least expensive fence. So now we're going to plug it in to the cost, right? So I have a 6x, so 6 times 200 plus 24,000, let's just do it this way, 240,000 divided by 200 squared. And that's going to give me 2,400. All right. Next question. A local club is arranging a charter flight to Hawaii. The cost of the trip is $577 each for 82 passengers, with a refund of $5 per passenger for each passenger in excess of 82. All right, so what we're going to do is we're going to try to come up with a cost function. So I know that it costs $577 per person, but we're going to take off $5 per person when there are more than 82 people. All right, so 5p and then people minus 82. So see if this makes sense. If there are 83 people, then this would give me 1 times, that would give me 1 passenger times, times that 5, right? If I had 84, then I would have 2 that would have to take off 5, and so on. All right, so here's my cost function. So 577p minus 5p squared plus 5p times 82, which is 410, which gives me 987p minus 5p squared. All right, this is what we want to maximize. So let's take the derivative, and I get 987 minus 10p, set this equal to 0. 10p equals 987. So p is going to give me 98.7. All right, we can't have 8.7 passenger or 0.7 of a passenger. So we're going to have 99 passengers. The maximum revenue, you're just going to plug that into my revenue. Why did I call this cost? This is a revenue function. Plug it into my revenue function. So R of 99 is going to be 987 times 99 minus 5 times 99 squared, right? Which is going to give me 48,708. All right. Next question. For the cost and price functions below, find the number Q of the unit that produces maximum profit, the price P per unit that produces the maximum profit, and C, the maximum profit P. All right, so I have a cost function here and a price. So I need to come up with the profit, all right? And we know that profit is revenue minus cost. All right, and my revenue is going to be Q times P minus C of Q is my cost. So I have Q times 65 minus 2Q minus C of Q, which is 70 plus 13Q. So I have 65Q minus 2Q squared minus 70 plus 13Q. So that gives me, what's 65 plus 13 is 78Q minus 2Q squared minus 70. Did I forget to distribute? I did. I forgot to distribute my negative sign. So minus 13Q. And that's going to give me a 52Q. All right, so this is my profit function in terms of Q. Let's take the derivative. So I get 52 minus 4Q. Set that equal to 0. So I have 4Q equals 52 and Q equals 13. So that's the number of units. Now they want the price per unit. So we're going to plug that into our price function. So 65 minus 2 times 13, which gives me 39. And then they want to know the maximum profit. So we're going to plug that into our profit function, which is 52 times 13 minus 2 times 13 squared minus 70, which gives me 268. And I believe that's my last question. So I hope that was helpful. Best of luck to you guys. Have a good evening. Good happy Easter.